So this is, don't look at this, it's engineering science. 143. So this is an exam number 4 from fall of 2011. So like always, you're going to get your geometry, which includes both where the centroids are, um, areas, and moments of inertia. Okay. This exam is beams for the most part. So we have beams. And when we have a beam, okay, we're going to have a normal stress from bending, okay, and that's tension compression. And shear stress, which we look at the longitudinal, it also technically comes from bending. Um, and it's, we don't really look at direction. So when we look at, as we have deformation, we might have compression on top, tension on bottom, and this would be from a positive moment. With a negative moment, we have tension top, compression bottom. So that's important because this will give us a negative normal stress. This will give us a positive normal stress. Okay. This will give us a positive normal stress, tension. This will give us a negative normal stress, compression. Normal stress, it's a function of the moment, which if you're either going to be given the moment or you're going to look at a shear like a moment diagram, calculate the largest moment. C. C is a distance from centroid to top or bottom. That is our maximum, okay? We could also say y, and y would just be that linear distance away from the centroid, okay? But once we get all the way to the top, it becomes c, or all the way to the bottom, it becomes c. So that's why we have 0 normal stress here at the center. We're transitioning from compression to tension, or tension to compression. And right here, those fibers are not changing any length. There's 0 strain, okay? 0 strain, 0 stress. So we need to remember how to find moment of inertia of a complex system. And before we can find moment of inertia, we have to be able to find our centroid, okay? We also looked at composite. Composite. That is where we have more than one material. So we might have a beam where maybe we have a steel plate on top of a wood beam. We have 2 materials and we need to transform into one material. This equation just is considering one material. So the one that's on top is the one we're changing. The one on the bottom is like our common denominator. Common denominator, we're changing everything into a common denominator. This is what we're changing into. Okay, so if we've changed the top, because denominator, common denominator, if we're changing the top, our new width is b times that n. Okay, so it can either get bigger or it can get smaller depending on this ratio. When we do that, we have to draw an entirely new cross section. Okay, so if this was my cross section, steel at the top, steel is a lot stiffer than that wood, so we are going to have a new width. Okay, we are not changing the height because we have bending about this axis. Okay, if we were bending about this axis, which we haven't looked at, it would be a whole different story. Okay, our base is the one that changes our base. So you can see if we were bending this way, we would be changing the base. Okay, but we are bending about that axis. So we now have a new centroid because behaviorally it acts like a T-beam, not just a rectangular section. So we would have to calculate that centroid using y bar and moment of inertia. And I know at my centroid right here, I have 0 stress. Okay, so if I wanted to know the maximum stress in this top piece, I'm going to have to go C to the top. So that's basically like y bar to the top. Okay, normal stress my over I. So at this point at the top, our maximum for that top piece is going to be n because that's the one we transformed. So we have to pull that n out. M C to the top over I, and that's going to be like my Y bar to the top. If I want to know the minimum stress that's in this top piece, okay, that's where I would just use Y. Okay, so instead of going all the way to the top, it would be to the top minus the thickness. Okay, that would be Y. When I look at this piece, material number 2, if I have a positive moment when I go to the top here, it's a compressive stress. When I go to the bottom here, it's tensile stress. So the top would not be C, because that's all the way, that would be my Y bar. We're just going to the top of the material. When I go to the bottom, it would actually be that Y bar to the bottom. Okay, these equations would just be my over I. The piece that I changed has to include that in. It's like we're pulling it back out. So then we have shear. So when we have a shear moment diagram, this comes from the moment diagram, this comes from the shear diagram, and our shear diagram is going to be 0 at the top and bottom, okay, 0 at the top and bottom, and maximum here at the center. So it's like opposite our bending. And that's because as we're bending, if we didn't have these pieces combined, they would end up sliding against each other to make that curve. When they're combined, we're having to hold them together. And so that's why at the middle, you're going to have that largest shear stress because it's the largest area. So Q is the first moment of an area. And when we hear the word moment, we're going to think of a distance. Okay. And the distance is always centroid to a centroid. So if I were looking at a T-beam, and here's my centroid, okay, here's my centroid, Q max is going to occur where I'm going to have shear max right here at the centroid. And I can either go to the bottom, so I could look at all of this, that's my area, and then my Y is from the centroid of this area to the centroid of the hole. Or I could look up here. I could take all of this area times this centroid plus this area times this centroid. It's super simple. We can divide up our areas and just multiply by centroids always back to the centroid of the hole. We always work with centroids to centroids to centroids, okay? Thickness is going to be the thickness of the fiber I'm looking at. If I'm looking here at my centroid, it's going to be the thickness, okay? If I'm looking here in the middle of the top part of my T, then that would be my thickness. Okay, so again, V is going to be constant for the whole cross section. I is the same moment of inertia here. T is just at where am I looking for my shear stress? Q is the distance beyond, which is why it's 0 at the top or 0 at the bottom, because when I go beyond the top or beyond the bottom, there's no area, so Q is 0. Little q is shear flow. Okay, so little q is VQ over I. This has to do with connections. And another way to look at shear, so if you think of shear flow, it's a force per spacing. So we could also call Q the force of the fastener that it can hold divided by the spacing of the fasteners. So if I have a nail that can hold 150 pounds, then 150 pounds per nail divided by the spacing equals the shear, the Q, which is the area we're nailing on, and then I. And we'll see thickness doesn't come on here. We're dealing with spacing, okay? Then we have this right here, this pressure vessels. And remember, if we have a cylinder, okay, so we have a cylinder, so it's not spherical, but it's cylindrical, then our stress one is our hoop, okay, and our stress 2 is our longitudinal. And I don't know how you want to remember this. Stress 2 is longer maybe than stress 1. Stress 2 has a 2 on the bottom, okay? And so when we look at these equations, stress 1 is always going to limit, because stress 2, with that 2 dividing factor right here, we are reducing that hoop stress, or the primary stress. We are reducing it by 2. If we have a perfectly circle container, spherical, it is the most, think of it, it's the most efficient shape. You don't see them very often because they're much harder to make than a tube. So this is all going to be stress 2, stress 2, stress 2, stress 2. It is all the longitudinal. It's super efficient. It's the smaller stress. So make sure you understand what goes on in each of these equations.